This video, I'm going to prove some facts about the phi function. If you like watching mathematical proofs, you should consider subscribing to my channel, as this is what we do here. We prove mathematical theorems, lemmas, corollaries, etc. Now, before I get into the proof, let's talk about what the phi function is. Like phi of 15. So it's asking you to consider all the numbers from 1 to 15. Don't say 15 when you're writing numbers. And phi of 15 is the number of numbers from 1 to 15 that are relatively prime to 15. 15 is just 5 times 3. So I can cross off all the numbers on the 5 times table, and I can cross off all the numbers on their 3 times table. 15 gets crossed off twice, and I'm left with 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers from 1 to 15 are relatively prime to 15. For example, the GCD of 8 and 15. This is made up of just powers of 2. This is made up of powers of 3 and 5. They have nothing in common. So that will count as one of the numbers for phi of 15. So it'll be one of those 8 numbers. And if you look at the GCD, say, of 9 and 15, this is made up of 3's, and this is made up of 3's, and this is made up of 3 squared, or 2 3's. This is 1 3. So they both have as 3 in common. It's not 1. Don't count 9 as one of the numbers that are relatively prime to 15. It's just basically just count the number. So if you have phi of n, you consider the numbers 1, 2, 3 up to n, and you count the numbers that are relatively prime to n. In this problem, I want to first prove that if n is even, then phi of 2n is 2 times phi of n. Okay, so n is even. This is proof of the first one. That implies that n is 2 to a power times m, where there's no 2's in that m. That is, the GCD of 2 and m is 1. I want to be able to use the fact that the phi function is multiplicative. So phi of 2n is equal to phi of 2 times n, which is 2 to the k m. But that's phi of 2 to the k plus 1 times m. This is just phi of 2 to the k plus 1 times, I meant to say phi, times phi of m, because these two numbers are being multiplied and they're relatively prime. Now, we should recall that phi of our prime number to the k power is that same number minus p to the k minus 1. So you have 2 to the k phi of, or phi of 2 to the k plus 1, so that's 2 to the k plus 1 minus just 2 to the k. And this is times phi of m. So let's get rid of this scrap work. Now, from here, I want to factor out a 2. I'm very motivated to do that because I want that 2 to come out in front. So I'm going to factor out a 2. I'm not going to touch that 2. In fact, I'll put it in red, except it didn't listen. There's that 2. Sometimes when you want to do proofs, you have to make it happen. So I pulled out a 2. I may not even have any idea why I did it, but sounds good to me. And then I say, ah, I see it. That's phi of 2 to the k. That's phi of 2 to the k times phi of m. Phi of 2 to the k times phi of m. Since 2 to the k and m are relatively prime, so we still have that red 2 in front, and when I multiply, I get phi of 2 to the k times m. But you know what? That's n. Phi of 2 to the k times m is phi of n. So yep, phi of 2n is equal to 2 times phi of n if n is even. Now, part 2. If n is odd, the 2 disappears. The 2 just disappears. Proof of 2. N is odd. That means n does not have any powers of 2. This implies that 2 does not divide n. Okay, so we have phi of 2. 2 does not divide n. Since 2 and n are relatively prime, the GCD of 2 and n is 1, I can just say this is phi of 2 times phi of n. There's the phi of n. What's phi of 2? Well, 1, 2. The only numbers that go into 2 are 2 and 4 and 6. It's 1. Phi of 2 is 1. And 1 times phi of n is phi of n. The next one says if 3 divides n, then this 3 can come out in front. Proof of 3. 3 divides n. That implies that n is 3 to the k times m, where m has no 3's in it. If it did, I'd put it, I'd make that power larger. Okay, so now, what is phi of 3n? Well, phi of 3n is 3 times n, 3k times m. That is, it's phi of 3 to the k plus 1 times phi of m. Now, I need to get rid of that phi, because I have to somehow factor out a 3. Need to get a 3 in front. And I'm not going to get it from the m, because m doesn't have any 3's in it. So this is equal to 3 to the k plus 1 minus 3 to the k times phi of m. Just make things happen. Pull out a 3. So we get 3 times 3 to the k minus 3 to the k minus 1 times phi of m. Now, I have the 3, I have the phi of m. Somehow, that has to be phi of 3 to the k, because 3 to the k times m, that's n. And it is. It is. Phi of 3 to the k is always that same number minus 1 less in the power. So what we have is this 3 times this, which is phi of 3 to the k times phi of m. And these two are relatively prime. So phi of this times phi of that is phi of this times that. But that's n. So 3 phi of n. This is equal to this, which equals that, which equals that, which in turn equals that, which equals that, which equals that, which ultimately equals this. That is, phi of 3 to the n is 3 times phi of n. Now, for the last one, if 3 does not divide n, then the 3 comes out as a 2. Proof. 3 does not divide n. That's given. So, phi of 3 times n. So this here implies that the GCD of 3 and n is 1. So phi of 3n is phi of 3 times phi of n. And if you want this to be 2 times phi of n, that's going to be 2. And if you don't believe it, you write down the numbers from 1 to 3, and you cross off the numbers on the 3 times table. Oh, phi of 3 is 2. But it had to be. It had to be. If this theorem is true, then it had to be true. And I'm almost positive I completed all of these. If you like seeing math like this, consider subscribing to my channel. See you guys in the next video. Click the like button. Don't forget, watch and learn.